To our last section in Unit 7. This is Learning Target 7C, Exponential Functions. By the end of this lesson, you will be able to graph exponential functions by creating a table of values and plotting the points. You will also be able to determine if an exponential function is an example of a growth or decay function, and then compute the initial amount and the growth or decay factor. So let's start with what an exponential function is. An exponential function is a function of the form y equals a times b to the x, where a does not equal 0, otherwise we just end up with 0. B is bigger than 1, or bigger than 0, bigger than 0 but not equal to 1. So we want the base of our exponent here to be a positive number, but we don't want it to be equal to 1, otherwise we would just end up with the function 1, which would be pretty boring and wouldn't actually give us the shape that an exponential function has. Let's look at a couple examples. So one example could be y equals 2 to the x. This is an example of an exponential function where our a value is 1 and our base is 2. Another example of an exponential function could be y equals 5 times 3 to the x, where the 5 is our a value, so it's our coefficient, and our 3 is our base of our exponential function. Now it doesn't just have to be integers, we could also have y equals 1/5 all to the x. So in this example, our a value again is 1, and our b value is going to be 1/5 then. So as long as our base is a positive number that is not equal to 1, it will work. Another example could be, we could write f of x equals 7 times, let's do 1/2 to the x power. So here, f of x, remember, is our function notation that we can use to replace y. So instead of writing y equals, we could write f of x equals. Now that function notation is used especially to identify the name of the function, which is f, and to help us remember that x is our independent variable. So we're subbing in our x here into our f of x, which means I'd sub it into my exponent. In this exponential function, 7 is our a value and 1/2 is our base or our b value. Let's look at our first example and see what a graph of one of these would look like. We're going to graph y equals 3 times 2 to the x, and we have a couple 5 points that we're going to end up plotting. Let's start with x equals -2. When I sub that in, I get 3 times 2 to the -2nd. We learned in Learning Target 7A how to simplify when we have negative exponents. We also have to take into account order of operations, which tells me that I have to simplify that exponent before I can multiply by the 3. Anything to a negative exponent can be rewritten as that number to the positive exponent. So we can rewrite 2 to the -2nd as 1/2 squared. We can simplify 1/2 squared, which will give us a 4th, and then 3 times a 4th is going to be equal to 3/4. On the left side over here, I'm going to keep track of our coordinate pairs for us. So we have 2, 3/4. Let's do our next value. So we get 3 times 2 to the -1st. Why don't you guys pause the video, simplify that, and then we'll check it together. Okay, order of operations tells us to simplify the exponent first, which I can rewrite as 1/2 to the positive first power. And then 3 times 1/2 will give us 3/2. So this will be equal to -1, 3/2 will be our next point. For x equals 0, we get 3 times 2 to the 0 power. Anything to the 0 power, remember, is equal to 1. So I get 3 times 1, which will give us 3. So we get 0, 3. When we substitute in 1, we get 3 times 2 to the first. Anything to the first power is just itself, so 3 times 2 will give us 6. So I have a 4th point here. Why don't you guys pause the video and simplify our last value for us. We have 3 times 2 to the 2nd. 2 to the 2nd is going to be 4. Remember, we have to simplify the exponents first before the multiplication. Then 3 times 4 will give us 12, and we get 2, 12. Okay, let's look at plotting these values now. So on our graph, I'm going to use each of these tick marks on the graph paper to represent one interval. And I'm going to start with the integer values. So let's start with 0, 3. I'll be up 1, 2, 3, that will be 0, 3. Then for 1, 6, I'll go to the right 1 and up 6. For 2, 12, I'll go to the right 2 and then up 12. So this was 6, 7, 8, 9, 10, 11. A little bit, we ran out of graph paper, that's okay. It would be the next point up there. Now for the fractional values, we can still plot them, they just might not be exact. So -1, 3 halves would be to the left 1, and then 3 halves is equal to 1.5, so it would be halfway between 1 and 2. Then -2, 3/4 would be below 1, since 3/4 is less than 1, so I'm going to put it about there. So we have 5 points so far. This is not creating a straight line, so exponential functions are not linear. So we're going to have some type of curve here, and we have to figure out, well, what will that curve look like? Let's think about what happens if you start plugging in larger numbers. So if we plug in larger numbers into our exponent, so if I plug in 5 or 10 or even 100, I'll end up with 2 to an even higher power, which means I'm going to end up with larger and larger numbers each time. So this graph, as it keeps going over to the right, it is going to keep going up as well. So I'm going to try my best to graph that on here, but that does keep going up to the right. We have to figure out what's going on to the left side though. So there's a couple things. Could this curve back up? Could it kind of go flat? Could it maybe dip down? We know it has to be a function, so it definitely has to keep going to the left, but we're not exactly sure what the shape will be. Why don't we test another negative value? So I'm going to have us substitute in x equals -5. We would end up with 3 times 2 to the -5th, which we could simplify to be 1 over 2 to the 5th power, which would give me 3 times 1 over 32, and then I would get 3 over 32. Now 3 over 32 is giving us an even smaller number than 3/4. So out here at -5, we're getting even closer to 0 then, because these numbers keep getting smaller and smaller. The question would be then, well, it can't go back up because the numbers are getting smaller, but will numbers ever become negative? What do you guys think? Is there any value that I can plug in for x that will give me a negative y value out? In this case, I actually will never get a negative y value. And the reasoning goes back to what we learned in Learning Target 7a, that any number to a negative exponent will always be rewritten as 1 over that base to the positive exponent. So because all of our negative exponents are equal to really positive numbers, they're just small positive numbers, I will always end up with positive values, which means this graph actually continues off to the left and it gets closer and closer to 0, but it actually doesn't touch x equals 0. So I'm trying my best to graph it on here, but it does get smaller and smaller and smaller, and it does what we say, it approaches 0. So this graph gets really, really close to the x-axis, but it never crosses or touches that x-axis, because no matter what my exponent is, it will always be rewritten as 1 over 2 to a positive number. So I can never get 0 and I can never get a negative number. Now when you take Algebra 2, you guys, in that class, we talk about exponential functions a lot more in detail. So one of the vocab words we talk about is what an asymptote is. So in Algebra 2, this will get defined and used a lot more. We're not going to worry about it too much, but I do want to introduce the word to you guys. So an asymptote is a line on a graph that graph never touches or crosses. So here we have what we call a horizontal asymptote on the x-axis. So in this case, we have an asymptote right there. If you've ever seen graphs with dotted lines drawn on them, those represent asymptotes. So on these exponential functions, we're going to see in every example that we do today that we'll have a horizontal asymptote at y equals 0, or at the x-axis. And the reasoning behind that is because this graph is never going to touch or cross the x-axis, since all of my y values will still be positive numbers. Okay. There's our first example of an exponential function. Let's look at another one and graph it. So we have y equals 4 times 1/2 to the x value. Let's sub in -2. So I get 4 times 1/2 to the -2nd power. Now, we've dealt with negative exponents before. Remember, you flip it. So if I scroll back up to the prior problem, we flipped 2 and rewrote it as 1/2 to that exponent, which means when we flip 1/2 then, we're going to end up with 2/1 to the +2 then. From here, we can simplify our exponents. I'm going to write up above the graph. We'll get 4 times 2 squared will also be equal to 4. Then 4 times 4 will give us 16. So our first coordinate pair on this graph will be -2, 16. Let's simplify the next one. So we get 4 times 1/2 to the -1st. Again, to simplify that negative exponent, I need to flip my base. So instead of 1/2 to the -1st, I'll end up with 2/1 to the +1st. So I have 4 times 2, and 4 times 2 will give us 8. So we have our next coordinate pair. For our third one, we get 4 times 1/2 to the 0. What will this simplify down to be? So 1/2 to the 0 power will give us 1. 4 times 1 will give us 4. So we get 0, 4. On our fourth point, we have 4 times 1/2 to the first power. That's the same thing as just 4 times 1/2, which will give us a value of 2. So I have 1, 2 then. On our last point here, we have 4 times 1/2 to the second. We can simplify this by distributing that exponent to each piece. So distributing it to the numerator, I'd get 1 squared. Distributing the 2 exponent to the denominator would give me 2 squared. 1 squared is just going to be 1, but 2 squared will give us 4, and then 4 times a fourth will be equal to 1. So I also have the coordinate pair 2, 1 then. Okay, let's graph these this time. So again, I'm going to use increments of 1. So 2, 16 won't actually fit on our graph, but we can graph everything else. So I'll start with -1, 8. So -1, 1, 2, 3, 4, 5, 8 up here. We then have 0, 4. I have 1, 2, so right 1 and up 2. And then 2, 1 will be left 2 and up 1. And if we were to graph -2, 16, it'd be something, let's say, like way up here, maybe even a little bit higher. Now, when we go to connect these, we have to think about what this shape will be that we're creating. So if I plug in more positive numbers, so if I keep going to the right, when I plug in those positive numbers for x, what's happening is I'm raising the denominator, and I'm doing 2 to the 5th, 2 to the 6th, 2 to the 7th, and I'm making that denominator bigger and bigger. But overall, the fraction's getting smaller and smaller and smaller. So we're seeing something similar to the last example, where this time as we keep going to the right, this graph is approaching the x-axis, but it's never touching or crossing that x-axis. And as we keep plugging in more negative numbers, because that negative exponent, if we plug in a negative number here, is going to flip the base and make this 2/1 to the positive power, then these numbers are going to keep getting bigger and bigger and bigger. So this graph will go up to the left in that top left-hand corner there. We do have that asymptote again, but we just want to worry about creating this shape. If I look and I compare our first two examples, in example 1, it started close to the x-axis and it grew over time, versus in example 2, it did the opposite. It started really high and then it got smaller over time. These are both examples of exponential functions, but they're actually two different types of functions, exponential functions. The first one, in example 1, is what we call an exponential growth function, because this graph keeps getting bigger and bigger and bigger. So we could write that on the side, and we're going to call this an exponential growth. Sorry, issues with the pen there. So it keeps growing over time. In the second example, it's called an exponential decay because it decays over time, or it gets smaller. So they're both exponential functions, but one is growing because it keeps getting bigger and bigger, and the other one is decaying because it keeps getting smaller and smaller. Okay, let's look at example 3. So I think you guys should pause the video and find all of these points, and then we'll check each one. Okay, let's check our first value. So we have 1/3 to the -2nd. So this one's written in function notation this time. So with the f of x, remember it is the same thing as y equals, but what it's telling me is when I'm going to find f of -2, I'm plugging in that value for every single x. So that gets plugged in for my exponent just like we did if it was y equals. Since I have a negative exponent, I need to flip my base to make it positive. So I'll get 3/1 to the +2. And then 3 squared will be equal to 9. So we get -2, 9. For our next value, we have 1/3 to the -1st. Because of that negative exponent, we need to flip the base, and then it will be to the positive exponent. So 3 to the 1st will give us 3. So I get -1, 3. For our third value, we get 1/3 to the 0 power. Remember, anything to the 0 power is going to be 1. So we have 0, 1. And then for our fourth point, we get 1/3 to the 1st, which will just give us 1/3. Oops, so we have 1, 1/3. And then for our last point, we get 1/3 to the 2nd. Remember, we can distribute that exponent and make it 1 squared over 3 squared, which will give us 1/9. So our last coordinate pair there will be 2, 9. When we go to plot these, let's see, we have -2, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We have -1, 3. We have 0, 1, 1, 1/3. So that's really, really close to the x-axis. I'll draw that as close as I can, and then 1/9 gets even closer to our x-axis. So remember, those values with the fractions won't be precise, but we want to approximate them to the best of our abilities. From here, think about what the shape of this will make. How would you connect those together and get our exponential curve? So as this graph starts, I know that these points are going to connect together, and this one might be a little challenging because they're really close together. So let me try that again. So these guys are curving down. And then from the left side, this keeps going up over time as it keeps growing and getting bigger and bigger. Then from the right side, this gets closer and closer to the x-axis, but remember, it does not cross or touch that x-axis. It just approaches that value, because no matter what other values I plug in here for our exponent, 1/3 to any positive number is going to just give me a really small positive number. And then as we plug in negative values for x, the fraction will flip, become 3/1 to the positive number, so those will keep getting bigger and bigger and bigger. So here is another graph of an exponential function. So this graph, would this look like that exponential growth, like in example 1, or the exponential decay in example 2? So this is another example of an exponential decay, because as we read the graph from left to right, the values are getting smaller and smaller and smaller as they approach 0. Okay, let's compare an exponential growth to an exponential decay and talk about how we were able to find it. So I want to keep our examples on the side over here. So from example 1, where our function said y equals 3 times 2 to the 2nd, and this gave us a growth. And then in examples 2 and 3, I need the y equals first. We had y equals 4 times 1/2 to the x, and we said that that was a decay since it kept getting smaller and smaller. And example 3, we had y equals, or f of x equals 1/3 to the x, and that was also going to be a decay. So let's look at these kind of side by side. So any function of the form y equals a times b to the x, remember that's an exponential function. what's going to make the difference between a growth and decay is the value for b. So if b is bigger than 1, remember our b is our base, then this will be what we call an exponential growth, and we say that that base b is called the growth factor for this function. So if I look at example 1, our base here was 2, which I could have looked at from the beginning and said since the base, which is 2, is bigger than 1, then this graph should be an exponential growth. The other piece of information that we can get from the exponential equation is the initial amount. So this a value here is what we call the initial amount, which will also always be our y-intercept if it's assuming we're of the form a times b to the x. In an exponential decay, that still is of the form y equals a times b to the x, since this is an exponential function. The difference now is that b, our base, is a value that is less than 1 but bigger than 0, because all bases have to be positive. So now we get a number in between 0 and 1. This is what we call an exponential decay, and our graph would go down from the left down to the right, like we saw in examples 2 and 3. And if I look at these, in example 2, our base was 1/2, which is less than 1, so that's why it was an exponential decay. And in example 3, our base was 1/3, which is also less than 1, so that's why example 3 was an exponential decay. So our base here is going to determine if we have a growth or a decay function. So an exponential growth will happen when our base is bigger than 1, and an exponential decay function will happen when our base is in between 0 and 1. And just like for a growth, we call the base b a decay factor in this case. Likewise, a is still our initial amount, which happened to also be our y-intercept for any decay function. So you can go back up to the prior examples and we can see that in example 1, we switch over to a pen and switch colors, that our a here was 3 and I got a y-intercept which was 0, 3 in example 1. And if we scroll back up and we check it, that did happen. 0, 3 was our y-intercept here. That also happened on example 2 with our a value being equal to 4. So here our a value is 4, so our initial amount is 4, and that gave us a y-intercept of 0, 4. If we double check that with our graph, up here, yes, 0, 4. And the reason that happens is because no matter what your base is, if I plug in 0 for my exponent, anything to the 0 power is going to be equal to 1, so I get a times 1, which is why a is what we call the initial amount. And that happens when we plug in x equals 0. In example 3, our initial amount is kind of invisible. It's that invisible 1 in front of it, but I still have an initial amount there of positive 1. Okay, in our last couple examples, what we're going to do is identify if it's an exponential growth or decay, and then find the initial amount and the growth or decay factor. So we're not going to graph any of these. We want to be able to find this information just by reading the equation. So let's look at example 4. It says f of x equals 8 times 4 to the x. I'm going to start with our initial amount. So I'm going to shorthand amount with a and t. So for our initial amount, remember we're looking for that a value. So which one of these is our a value? 8 or 4? Our a value here is going to be 8, so our initial amount will be 8. Now we have to decide, is it a growth or a decay? So to figure that out, we want to look at the base. So our base in this example is 4, and since 4 is bigger than 1, so our base here is 4, and since 4 is bigger than 1, we have an exponential growth, and then it's growing by a factor of 4. So that last part was to determine the growth or decay factor, and that is just whatever the numerical value of the base is. So in this first example, we had an initial amount of 8 and a growth since our base was bigger than 1, and it is growing by a factor of 4. Okay, let's look at example 5. What is your initial amount in example 5? Our initial amount in example 5 is going to be 3, since that's the a value in front. Our base here is equal to 1/4. So what do you guys think? Will this be an exponential growth or an exponential decay? We will have an exponential decay in this case, since our base here is less than 1, and it is decaying by a factor of 1/4 then. So remember that factor that it's either growing or decaying by is just the base value. Okay, why don't you guys pause the video and do example 6 on your own first. Okay, in example 6, we have an initial factor, or an initial amount, of 1/2. This is an exponential growth, since our base, which is equal to 5, is bigger than 1, and it is growing by a factor of 5. Let's do example 7. In example 7, what would our initial amount be? So this time, I don't have a number in front, but that means that I have that invisible 1 in front, so our initial amount is going to be equal to 1. This is a decay, decay by a factor of 1/200. Of 1/200. All right, you guys. And the reason I know it's a decay is because 1/200 is my base, and that is definitely less than 1. Okay, why don't you guys pause the video and try example 8 on your own first, and then we'll check it. Okay, in example 8, we have an initial amount which is going to be equal to 1.47. So yes, a decimal amount, but that's okay. It is going to be a decay, and it's decaying by a factor of 0.34. And the reason I knew it was a decay is because that base, which is our 0.34, is less than 1. Let's do example 9. So in example 9, we have an initial amount of 1. Remember there is that invisible 1 in front. This is going to be a growth, and it's growing by 10, since our base value is equal to 10, and 10 is definitely bigger than 1. Why don't you guys pause the video and do 10 and 11, and then we'll check both of them. In example 10, our initial amount is going to be equal to 2, since that's our coefficient in front. And we have a decay this time, and it is decaying by 3/4. And the reason it's a decay is because that base is less than 1. And our last example. In example 11, we have an initial amount which is going to be equal to 1/3, since 1/3 is our coefficient. Do you guys think 11 will be a growth or decay? 11 is going to be a growth, and it is growing by 5/2. And the reason it's a growth is, although 5/2 is a fraction, 5/2 though is still bigger than 1, and it doesn't matter if it's a fraction, an integer, or decimal, we have to see, is that base bigger than or less than 1? So because 5/2 is equal to 2.5, that is definitely going to give us a number that is bigger than 1, so this will be a growth. So this is the end of Unit 7. In this video, we learned how to graph exponential functions of the form y equals a times b to the x by plotting some points and then graphing those. We learned that the graphs are going to stay above the x-axis when they're in this form, since we have that horizontal asymptote. We also learned how to identify if we have an exponential growth or an exponential decay function just by looking at the original equation and looking to see, is that base bigger than 1? Then we'd have an exponential growth, or seeing if that base is less than 1, and in that case we would have an exponential decay.